Welcome back. In the previous video, we looked at the principle of work and energy. The principle of work and energy, we showed that it is not a fundamentally new law of nature. Rather, it is Newton's second law expressed in a different form. That is, it is the integrated form of Newton's second law, which states that the net force on a body is equal to the mass times the acceleration vector. Now, for a rigid body, what we looked at, we investigated what the kinetic energy would look like. And what we saw is that for a rigid body, there is an additional form of kinetic energy, that being the rotational component here. So a rigid body, which can be undergoing general planar motion, would have two possible components of kinetic energy. The first one being the translational one, and the second one, the rotational component. And what we see is that the translational one is the component that we are familiar with. Okay? However, we must specify at which point the velocity is evaluated. So we know that for a particle, the kinetic energy is 1/2 mv squared. As we saw in rigid body kinematics, a rigid body can have different linear velocities at different points on the body. So here what we say is that the translational component of kinetic energy uses the velocity at the center of mass, which we denote as g. Furthermore, what we see is that there's a direct analogy between the translational and rotational components, where they are both 1/2 multiplied by something that is dependent on mass and multiplied by a certain velocity. Now, this ig is the mass moment of inertia, which is not the mass, but rather it is the distribution of the mass about a certain point. And in this case, that point or that axis is the axis passing through the center of gravity, G. Okay, so what we're going to do here is look at a few special forms of the kinetic energy. Okay, so the first one we're going to look at is translation. So if you remember from rigid body kinematics, translation, if we were to draw a line between 2 points on the rigid body, that line will not change its orientation between 2 points, essentially between position A and position B of the rigid body. Okay, so as it moves in space, that line connecting 2 points maintains its orientation. So for translation, what we have is omega is equal to 0. There is no angular velocity. Okay, so this just simply reduces to t is equal to 1/2 mvg squared. Fairly straightforward. The kinetic energy of a rigid body rotating about a point O has both a translational and a rotational component of kinetic energy. Okay, so if we were to draw some generic rigid body here, it is fixed here at point O, and let's say that maybe our center of mass is G over here. Okay, what will we have? Well, we know that our center of mass will have a velocity vg. Okay, so I mean we can still express this as t is equal to 1/2 mvg squared plus 1/2 ig omega squared. There's nothing wrong with that. Okay, so I'm just going to add here that we might have, well, we definitely do have an angular velocity omega. However, if the axis of rotation happens to coincide with the center of mass g, then Vg will be equal to 0, and you will only have the kinetic energy being 1/2 Ig omega squared. However, if the rotation is about a point other than g, such as shown here, where the rotation is about point O, then what we can say is that Vg is equal to omega Rg. And this we know from fixed axis rotation. So Rg is the position vector connecting the axis of rotation and whatever point we're interested in finding the linear velocity v. Okay? So what we can say here is that t is equal to 1/2 m, and then what we would have here is omega squared Rg squared plus 1/2 Ig omega squared. Which we can rearrange as 1/2, and then we will have Ig plus mRg squared multiplied by omega squared. And hopefully what you can notice here is that this is the parallel axis theorem. Okay? So recall, the parallel axis theorem states that if we know the mass moment of inertia at a certain location, so in this case, let's say we know the mass moment of inertia at location G, the center of mass, so the mass moment of inertia about an axis passing through the center of mass, we can find the mass moment of inertia about another point, a distance r away, using the parallel axis theorem. So in this case, what this is doing is giving us the mass moment of inertia about an axis rg away, and that axis is passing through point O. So we can just say that this is t is equal to 1/2 I-O omega squared. Okay, so we can simplify for fixed axis rotation our original equation for the kinetic energy by noting that we recover the parallel axis theorem, and so therefore we can just calculate t as being equal to 1/2 I-O omega squared, where I-O is the mass moment of inertia about an axis passing through the axis of rotation O. And what we'll notice is that this is actually a very useful form once we start solving problems. All right, so we've spent some time looking at the kinetic energy term in our principle of work and energy. Now it's time to turn our attention to the work. There are different forms of work, and we're going to look at a few that are applicable to planar dynamics. In the most general term, the work done by a force on a body is equal to the force multiplied by the displacement of the body. So let's write that out. Force multiplied by displacement of the body. That is, if a force is applied over a distance and the final location is different from the start, then work is being done. The work done by an external force acting on a body moving along a path S is given by this. So we have the work going from position 1 to position 2 is equal to the integral of the force vector multiplied by the dot product of dr, a differential displacement r. Now what does this mean? So again, what we're saying is that it's moving along a path S. Recall what the dot product is saying. The dot product is saying that we are projecting, or we're looking at the component of the force F in the r direction. Okay? So we can state this also as F cosine of theta ds, where ds is a differential displacement along the path S. All right, so if we have, let's say, a path, okay, and this path is denoted by S, we might have some force acting on a rigid body. So maybe let's draw a rigid body here, and this would be point 1, this would be point 2, and let's say we are applying a force here, and maybe a force like this. And so this is position 1, and this is position 2. Okay? So what this is saying is that only the component, so at this point here, we have a displacement in this direction over here. So only the component of the force vector in the direction dr is actually doing any work. Okay? And so again, recall that the dot product of two vectors is A dotted with B is equal to the magnitude of A multiplied by the magnitude of B multiplied by the cosine of theta. Okay? And this is precisely what we have over here. Okay? So we have the magnitude of F, the magnitude of dr, which is just the length or the arc length along the path S, multiplied by cosine of theta. Okay? So only the component that is in the direction of the displacement is actually doing work. And this angle theta is the angle between the tails of the force and differential displacement. Okay? So in the case of an external force with a constant magnitude, so if the force were constant, then we can take the force out of the integral. Okay. Similarly, if there is no change in direction, so if the force is has a constant magnitude and direction, then we can do away with the integral and just say that the work from 1 to 2 is just a force multiplied by cosine theta multiplied by the total displacement S. Okay? So this is the general form of work done by an external force on a rigid body. Now let's consider the work of a couple moment. Okay, so let's say we have a rigid body, and let's draw a line here, and let's say that we have a moment m which induces a certain angular displacement theta. Okay? So if a moment is applied to a rigid body leading to a differential rotation d theta, then the moment is performing work on the body. So in general form, the work due by the moment, or the work done by the moment, is the integral from theta 1 to theta 2, so the original orientation and the final orientation, of m d theta. So we're multiplying the couple moment by the differential angular displacement theta. So it's useful to perform a check on our dimensions. Okay, so recall that work is a force multiplied by a distance. So in SI units, this would be newtons multiplied by meters. These are the dimensions of work. So now in SI units, a moment has units of Newton meters. So this angular displacement will have to be in radians in order to maintain consistency in our units. So the work of the couple is positive when the moment and angular displacement have the same direction. Okay, and this is the same thing with the general form of work. Okay, so the work is positive when the applied force is in the same direction as the displacement. If the net displacement of the body is in the opposite direction of the force component along the path S, then the work done by that particular force will be negative. Next, we turn our attention to the work done by a weight. Okay, so I'm going to give you the general form, which is the work going from 1 to 2 of a weight is equal to the negative of mg y2 minus y1. And I'll let you think about this for a while as I draw this out. So let's say we have a rigid body which has a certain weight, W. And this is at the center of mass G. And let's assume that Y is positive upwards. Okay, so this is what we would call our datum. Now, let's say that at position 2, our rigid body is now in this position over here. Okay, so this would be y2, and this would be y1. Okay, so recall that the work is positive when the force vector and the displacement are in the same direction. So now, if a body is moving downwards and our positive sign convention is positive upwards. So if a body has moved downwards from position 1 to position 2, then y2 minus y1 will be negative. Okay? But we know by convention that the work is positive if the force vector and the displacement are in the same direction. Okay? So we need that negative in order to get a positive work. Okay? So if y2 is less than y1, then we could say that y2 minus y1 will be less than 0. Okay? But so therefore what we would need is this negative sign over here. So hopefully this is fairly clear as to why we're doing this. Okay? And we can notice too that if y2 is below the datum, this still works out as well. Okay? The final form of work that we're going to look at is the work of an elastic spring force. So recall that the spring force is always restorative. What we mean by this is that if a body attached to the spring is pulled or pushed, resulting in the spring stretching or compressing, the spring force on the body will always be in the opposite direction to the motion. So let's write this out. Spring forces are restorative. Again, what we mean by this is that a spring has a certain unstretched length. You can think of it as the length that it likes to assume, okay? And then we might either pull the spring or push the spring due to some displacement on that rigid body. So let's say we compress the spring. What is the spring doing on the rigid body? So we have, let's say, let's draw this out. So we have a spring force. Well, let's draw the body first. So body at position 1. And we'll have a spring force or a spring attached here, and then the body is at position 2 over here. So as we're compressing the spring, what the spring will do is actually push against the body. Okay, so our displacement S is in this direction, but our force of the spring is in this direction. So as we can see, the spring force and the displacement are always in opposite directions. So the spring acts to return to what we call its unstretched position. So we recall from Hooke's law that the spring force is equal to your spring constant multiplied by the displacement. So the spring will do work when it either stretches or compresses from S1 to S2. Okay, but whether stretched or compressed, the work will always be negative, since the force acts against the displacement of the body. Okay, so this is our force from Hooke's law. Okay, so our work will be this force multiplied by the displacement. And so what we have is that the work done by the spring will be equal to will be equal to the negative of 1/2 k S2 squared minus 1/2 k S1 squared. And this expression is applicable where the magnitude of S2 is greater than the magnitude of S1. Now you might be wondering where these 1/2 multipliers are coming from. Now recall that the work in its most general form is equal to F dotted with dr. And now for most cases, our force was constant along the displacement. So for example, for the work of a weight up here, the force due to the weight remains constant between position 1 and position 2. However, this is not the case with a spring. Okay, so with a spring, you have a force here, and let's say a distance x, and as we stretch, the force is increasing, right? So you've likely seen this before, where the slope is k. Okay, so your force is equal to kx. Okay, so between position 1, let's say position 1 is over here and position 2 is over here, the force has not remained constant. Okay, so we could express this as the work is equal to the integral of Hooke's law, which states that the force of a spring is kx and multiplied by dx, the differential displacement. And so naturally, okay, so the spring constant is constant, so we can take it out of the integral. We have k, but then we'll see that the integral of x dx is x squared over 2. And this is where that 1/2 multiplier is coming from. Okay? And we can express the work of a weight and the work of an elastic spring force in terms of potential energies. And you have likely seen this in previous physics courses. Okay? So, given a datum here, we could say that up here it has potential energy, and we could call this potential energy at state 1, and here it has potential energy at state 2. And you also likely recall that the gravitational potential energy, so again, potential energy is the potential to do some work. Okay? So work and energy have a certain reciprocal relationship. And you've seen that the gravitational potential energy has the form of mg multiplied by a certain height. And so what we see here is that the work done from u1 to 2 is equal to the potential energy, which we'll denote as v. And for gravity, we'll call this potential energy Vg. Okay, so the gravitational potential energy at position 1 minus the gravitational potential energy at state 2. And these are just mgy1 and mgy2. Okay, so the work done from going from position 1 to position 2 is equal to the change in the potential energy from position 1 to position 2. Similarly, when we are looking at an elastic spring, there is an elastic potential energy. And this potential energy is this term over here and over here. So what we can state here is that the work done from position 1 to position 2 is the elastic potential energy at position 1 minus the elastic potential energy at state 2. Okay? So again, potential energy is the potential to do work. Okay? So as we see, there is a reciprocal relationship between a change in potential energy and work done by a certain force. Okay, so we'll wrap up here, and we're just going to recap what we've done. So after having looked at the kinetic energy forms, we decided to look at special forms of kinetic energy for different types of planar motion. So we looked at translation, and we saw that for translation there is no angular velocity, so we only have the translational component of kinetic energy, which is 1/2 mvg squared. For fixed axis rotation, we saw that we can simplify our general form for the kinetic energy of a rigid body, and that simplified form tells us that the kinetic energy is 1/2 I-O omega squared, where O is the axis passing through the axis of rotation. Finally, we looked at the different forms of work that can be done on a rigid body. We looked at the most general form of work, which states that the work done by a force is equal to the component of that force acting multiplied by the displacement. And it's only the component of the force in the direction of the displacement that is doing work. We saw that, as opposed to particle dynamics, in rigid body dynamics, we can apply moments, and moments do work as well. And then finally, we looked at the work of a weight and the work of an elastic spring force, and we saw that these can also be expressed in terms of their potential energy.